University of Reading. Paul, as you can see, is going to talk about the impacts of stochastic noise on climate models.
Thank you. Good afternoon, everyone, and thank you for the invitation to speak. Oops, where's that gone? Come back. Right. So I'm going to talk about stochastic noise in climate models, and of course we in this room all know what the word stochastic means, but many less mathematically inclined colleagues sort of roll their eyes at the mere thought of this word stochastic. In fact, I've seen colleagues sort of throw their arms up and say it's all Greek to me, this stochastic stuff. And these colleagues are actually more right than they think, because in fact, if you trace the etymology of the English word stochastic, it has its roots in this Greek word. I heard someone pronounce it. I wasn't going to dare. But is it stochastikos? Oh, right. Good. But what's interesting about this word is that the literal translation into English is not stochastic or random, but rather, as I understand it, is it refers to guessing or aiming. So in other words, gambling is a better translation, yeah. So it refers to the process of having to make a decision in the absence of certainty, which I think is a very apt sort of description of the problem facing climate modelers, where of course the subgrid scale impacts on the resolve flow are not known with certainty at every grid point and at every time step, because they're in general not uniquely deterministically slave to the large scale flow, but rather are drawn or guessed at from some probability density function conditioned on the large scale flow. This is not going to be a very challenging talk intellectually, because it is Friday afternoon after all. And also, of course, the disadvantage facing any speaker in the final session of a week-long conference is that everything I wanted to say has already been said, actually, in one form or another. So I'm not going to say anything that hasn't already been referred to, either in detail or in passing. I'll talk about noise-induced phenomena in various bits of the climate system, noise-induced transitions in bistable systems, noise-induced rectification as a means of reducing mean climatological errors, noise-induced variability. All of these will be talked about. What is perhaps novel to this talk in the context of this meeting is that I'll draw inspiration from an unexpected quarter, namely a laboratory experiment which exhibits meta-stability and regime transitions, which have a plausible interpretation, as I'll show you, as being noise-induced transitions. And I'll also apply some of these ideas to bits of the climate system that have perhaps not been mentioned in detail so far, such as the polar stratospheric vortex, for example, and a possible interpretation of stratospheric vortex splits as a noise-induced phenomenon. I'll also talk about noise-induced rectification of the ocean mixed layer, and if there's time at the end, I'll talk about the excitation of El Nino ENSO oscillations in a coupled GCM, which is sufficiently coarse that it lacks ENSO oscillations in the absence of stochasticity. So that's what's coming. I'm going to structure the talk by breaking it up into these three broad themes: noise-induced transitions, rectification or drift, and variability. Talk first about the transitions as seen in flow regimes in rotating laboratory experiments, and then as a mechanism for stratospheric polar vortex splits. And I'll move on to noise-induced rectification. This is going to involve talking about Stommel's mixed layer demon. If you haven't come across that before, you'll be coming across it soon. And finally, noise-induced variability. As I mentioned, the excitation of El Nino oscillations in a coupled general circulation model that is too coarse to exhibit an ENSO cycle when it's run deterministically. Right, so, well, pictures like this have been shown in many talks this week. One is thinking about a bistable system with a sort of less stable and a more stable state. And of course, if in the absence of external noise, the system will sit here indefinitely, but one is interested in the possibility of noise kicking the system out into the other stable state. Plenty of examples of this in atmosphere-ocean science. Here's one. This is about the thermohaline circulation, the global scale ocean circulation. It's just a little cartoon of it here. It transports the heat of 1 million power stations or something north in the Atlantic, so it plays a crucial role in the climate of the North Atlantic European sector. And simple models, at least, such as the Stommel box model of this system, suggest that the thermohaline circulation is bistable and may therefore collapse if a sufficient amount of fresh water is put into the North Atlantic, for example. And there's a bit of a debate about whether this is an artifact of the very coarse representation in box models, and whether this bistability persists in more complicated models. But here's an ocean general circulation model study, admittedly with idealized continental geometry. And this is just showing the strength of this thermohaline circulation as a function of time over 2,000 years. One's further up is 1 million meters cubed per second. There are two integrations here. One, so this is an ocean-only simulation forced by prescribed surface fluxes. And when the surface fluxes do not contain a random component, in other words, when the model is run deterministically, and the amount of fresh water being poured into the North Atlantic is gradually being increased in time, eventually, it's just like this. This state loses its stability, and this becomes the only stable state, bifurcation, and the circulation collapses. But what's interesting is that when a stochastic or random component is added to the wind stress forcing, it collapses much earlier, which is exactly the sort of thing one might expect from this simple picture. So I'm going to talk first about some noise-induced transitions as seen in some laboratory experiments. These rotating annulus experiments have been run for very many decades, going back to the 1950s, I think. Raymond Hyde was a pioneer, an early pioneer. And the reason for doing these experiments is that there's a deep dynamical similarity between the fluid flow in a rotating annulus, bounded by this inner wall and the outer wall, and the fluid flow on the mid-latitude fluid flow on a rotating planet. There aren't these boundaries in the real world, of course, so the geometric similarity is perhaps not there, but the dynamical similarity is there. And much insight has been got into the evolution of large-scale flows in the real world, in the real atmosphere, from looking at laboratory experiments. This is the height, I think, of the 500 millibar pressure surface in the northern hemisphere. The North Pole's in the middle. So the flow follows these wavy sort of perturbed jet stream sort of structure. And in this rotating annulus laboratory experiment, it's being cooled at the inner boundary and heated at the outer boundary to mimic the equator to pole temperature gradient. And some red dye has been released at the start of the experiment around the outer boundary, and some green dye near the inner sidewall. And after a few rotation periods, this is what it looks like. And there's clearly a strong qualitative resemblance, at least, between the flow in the rotating annulus and mid-latitude atmospheric flows. Now, as I say, these experiments have been used for decades, but I think there's a bit of a view, perhaps, that they've had their day, and that perhaps they ought to be sort of confined to museums now and written about in textbooks with sort of fondness, but not actually run anymore, especially when we have sophisticated computational codes now. You can knock up a simulation, some code to simulate this flow in a few days or something. But I'd like to argue that there still is some value in studying these laboratory experiments. I mean, part of the value is because essentially the Navier-Stokes equations are being solved here with infinite resolution in a zero time step, with no numerical errors, no errors from finite precision or any of that. It's effectively an infinitely fast supercomputer, this tank of water. And furthermore, these experiments so far have been used just to study the large-scale flow, so baroclinic generation of eddies and baroclinic life cycles. What I'd like to do is to study interactions across scale-separated interactions between short-scale waves, such as these gravity waves in this experiment. I'll say more about this in a minute. Interactions between the short scale waves and the large scale sort of baroclinic wave. The idea is to sort of exploit the dynamic and partly the geometric similarity, and to try and say something about the interactions of these waves in the real atmosphere and also the ocean, incidentally, from observing the analogous interaction on a laboratory scale.
Really good argument, those are shear instabilities, I think, in the bottom picture as well.
Right.
Kelvin, how much for those?
So these are in noctilucent clouds. This is taken in Sweden, and I'm not sure exactly what the specific generation mechanism is here, but I'm going to talk about the impacts and less about the generation. I'll just sort of motivate this. I mean, these gravity waves, although they're short in wavelength and high in frequency, and there's not much energy in them compared to the energy in the global scale circulation, they do play a leading order role in determining the general circulation of both the atmosphere and the ocean by transporting momentum in the atmosphere vertically and depositing it in the stratosphere, and by closing the thermohaline circulation in the ocean, because the downward branch is sort of driven, if you like that word, by high latitude surface buoyancy loss, but it's the return flow that depends critically on mixing due to breaking gravity waves. So these waves are critically important in both the atmosphere and the ocean. They're ubiquitous in rotating stratified fluid flows. Some surface gravity waves here on the surface of the ocean. This is the light hill shipwake problem. But of course there are gravity waves internal to the ocean as well. It's just hard to find a photograph of them, so I sort of put this here as a placeholder. And finally, in the bottom right, this is a satellite picture of the Martian atmosphere. This is a crater, Korolev crater, poking its head up into the Martian clouds, and you see a wake of gravity waves generated downwind of the crater. I'll just show this movie. This is a satellite picture as well of the South Pacific Ocean with the equator more or less up here. This is a picture of marine stratocumulus clouds. The quantity plotted is the brightness temperature in Kelvin, which is a proxy for the height of the top of the clouds. And I don't know how well you can see this from the back. I'm not even sure you can see it very well from the front. In fact, I'm struggling. But there are some gravity waves in this picture, sort of propagating up from a disturbance at the bottom left of the picture. What's interesting about this picture is that you see these pockets of open cloud-free regions which grow over time. I think there's a frame once every 15 minutes or something, and this is taken over something like 2 days. These pockets grow in time. They're called pockets of open cells, and potentially they play a role in climate, because of course they will alter the balance of incoming and outgoing radiation. And in the opinion of these authors, thanks to Grant Allen at the University of Manchester for allowing me to show this, in the opinion of these authors, it is gravity waves which are opening up these pockets of open cells. So if you look closely at this, every time a gravity wave trough passes one of these open cellular regions, it appears to open it a bit wider. So this is a plausible generation mechanism for open regions, cloud-free regions in the marine stratocumulus cloud deck. There are other postulated mechanisms as well, but it is plausible, according to these authors, that gravity waves play a role. Of course, we can't investigate that in the laboratory, but we can investigate other gravity wave impacts on sort of fundamental rotating fluid flows that don't have clouds in them. I'm going to use this rotating annulus system to illustrate some of these points. I don't want to dwell on this, but this is in Peter Reed's lab in Oxford. And I'll just refer, I think, to this schematic. It's an annulus in which there are two liquids, two immiscible liquids actually. So there's a very well-defined interface. There's no mixing of these two interfaces. It's water and oil essentially. They have slightly different densities. They're on a rotating turntable to mimic the rotation of the Earth. And there's a camera looking from above and recording the flow in this experiment. So it's not forced by heating and cooling as some of the other experiments are, but rather by a differentially rotating lid, but the impact on the flow is qualitatively the same. And I should mention that these different, I don't want to go into this, but one of these liquids is optically active, and it turns out that if you view the system through crossed Polaroids, there's a correlation between interface height, so the height of this internal interface, and the colour registered by this camera. So when you see pictures like this, you can infer that the internal interface in the system is looking like this. So we're just looking here at waves on the interface. Right, so in very many experiments using this system, we classically see pictures that look like this. I showed you this before, much smaller. You see the coexistence of a large-scale wave which has grown from baroclinic instability and equilibrated at finite amplitude. And in the troughs, in the two troughs in this case of the large-scale wave, you see the emission of these short-scale inertial gravity waves. And I'm going to try and learn something about the impacts of gravity waves on the large-scale flow in the atmosphere by studying that analogous interaction on a laboratory scale in the first sort of 5 minutes of the next 5 minutes of the talk. For those of you who are YouTube enabled, there's a movie of this. Well, we're on the web, we're all YouTube enabled. Anyone who's on the web, you can see a movie of this at that website address, and I'll just briefly try to show you it now. If the technology works. I'm going to click on that. Right. Play. Just about. Right. So this is a picture picked up by that camera. Blue means a raised interface, yellow means a suppressed interface, and I'm talking about the impacts of these short-scale gravity waves on the large-scale flow, and I'm going to try and represent them by stochastic noise and try and convince you that that's a plausible representation. Now, this is a laboratory experiment that exhibits simple flow regimes, and these are regarded by many people as sort of prototypes for sort of flow regimes in the atmosphere. So don't worry too much about what these axes are. They're just two non-dimensional parameters that depend on things like the Coriolis parameter and the stratification of the fluid and the forcing at the upper boundary. When the fluid number is small, there's no baroclinic instability, because the criterion for baroclinic instability is that the fluid number has to be greater than pi squared over 2. So when it's too small, there's no instability and the flow remains devoid of waves. But as you increase the fluid number, which means increasing the Coriolis parameter, you see different flow regimes. A wave number 1 regime with one crest and one trough, and a wave 2 and a wave 3 regime. And these are sort of simple prototype flows for supposed regime behavior in the atmosphere, if indeed there is regime behavior in the atmosphere. So one has in mind perhaps blocking, for example. Right. And in fact, not only are there simple flow regimes, but there are parts of the regime diagram in which there is bistability. So if I go near the there it comes. If I go near the wave 1, wave 2 boundary, so if I run experiments within a sort of a certain distance of this boundary, there will be bistability between the wave 1 and the wave 2 regimes. And what we see from very many experiments on this apparatus is that it's possible to run the experiment with and without gravity waves by slightly changing the surface tension at the interface, for those who are interested in the technical details. Without gravity waves, the system just stays locked in its present state indefinitely. So a wave 2 state will remain locked into the wave 2 state forever, essentially. Well, I never watched them forever, but for many hours, for the many hours I sat watching these things go round, it would just stay there. I mean, the wave moves in the prograde sense around the apparatus, of course. So the highs and the lows propagate, but it remains a wave 2. In contrast, in flows where the gravity waves are present, and you see them here and here, sometimes, not always, but sometimes, the flow would spontaneously transition itself into a wave 1 flow. Not all of the time, but over many hours, there was a certain probability of a transition from the wave 2 to the wave 1 state being undergone. And I'm going to try and persuade you that that is I've called it a noise-induced transition, with noise in sort of inverted commas here. It's not really noise, of course. It's that these gravity waves are a signal. I mean, they're coherent in space and time. They satisfy a dispersion relation. They have a well-defined frequency and wavelength. But I will show you that we can mimic these transitions in a model through the addition of noise. Did you have a question, Tim? Thought I saw your hand go up. Sorry, no, right. So these are what are called the quasi-geostrophic equations for this 2-layer fluid. The gravity waves are filtered out of these equations by construction. Gravity waves depend fundamentally on ageostrophic advection, and there's no ageostrophic advection in the quasi-geostrophic equations because they're a low Rossby number approximation to the shallow water equations. And what I'm going to do is very, very crudely try to write down a stochastic gravity wave parameterization, the crudest conceivable gravity wave parameterization. I'm just going to add, and it is additive, noise, global, uniformly distributed, white, purely baroclinic noise to the right-hand sides of these equations to try to mimic the impacts of the gravity waves, which are filtered out of this model by dynamical construction. Now, ideally, one would go back and repeat these experiments with multiplicative noise. The gravity waves are stretching and compressing vortex columns, which is this h here, taken to be constant. Ideally, one would add noise to h, which would become multiplicative or state-dependent noise on the stream function psi. But for the moment, I have additive noise here, not state-dependent noise. Ideally, as well, one would localize the noise in space and time to match what we see in the laboratory. Here I've used global. And one might want to use something more sophisticated than uniformly distributive noise, and one might also want to put in correlations in space and time. This really is the crudest, simplest conceivable gravity wave parameterization in these equations.
It's white in time and uniform in space. White in space.
It's white in space and time, yeah, but drawn from a uniform distribution.
It's those signs that make it baroclinic.
Yeah, it's purely baroclinic because the gravity waves appear to be. I mean, if a yeah.
That's the plus and the minus.
That's right. Yeah, yeah. So the perturbations are equal and opposite in the upper and lower layers because an interface perturbation that moves upward will squash the upper layer but expand the lower layer. And that seems to work. We can mimic the transitions we see in the laboratory, which I think are the first example of a noise-induced transition in one of these rotating annulus laboratory experiments. We can mimic those transitions in this quasi-geostrophic model by the addition of that crude stochastic gravity wave representation. So we run with time here on the abscissa and azimuth on the ordinate. These are Hofmüller plots at mid-radius of the potential vorticity in the upper layer. And they show exactly what we see in the lab, which is that a wave 2 flow remains a wave 2 flow indefinitely, but when the noise term is activated, what starts out as a wave 2 flow with 2 crests and 2 troughs transitions into a wave 1 flow. And I think there's a movie of that. This is the stream function now. So the noise is less evident because the potential vorticity is a more highly involves derivatives. So the small scale features are more evident in it. But you see here this initially what is a wave 2 flow lose one of its crests and one of its troughs and become a wave 1 flow. And this is exactly what we see in the laboratory, apparently induced by the gravity waves in the laboratory, but by the additive stochastic noise in this experiment.
You're showing us the theoretical model there where you're not
Yes, that's correct. This is the model.
And without the noise, it will stay wave 2 forever in the model.
Correct. Yeah. I don't have a movie of it, but I mean this shows it. Yeah, stays there forever. I don't want to.
That's a cleaner experiment from the lab case where you've got to vary the overall conditions anyway, so it isn't quite clear what to do with the cavity.
Yeah, that's right. Yeah. I'm going to skip over these few slides, I think, because now I'm going to talk about sort of application, actually, of that sort of idea to a part of the climate system, in particular to polar vortex splits in the stratosphere. These are pictures of the potential vorticity on the, I think, the 550 Kelvin isentropic surface, so in the stratosphere. Red means high potential vorticity, green means low potential vorticity. We're looking down on the northern hemisphere with the North Pole at the centre. This is a time series in November 2001, starting on the 25th, 6th, 7th, 28th, 29th and 30th. And what happens, and this happens roughly annually in the Arctic polar vortex, is that what starts out as a dominantly sort of uniform, unperturbed zonal mean zonal flow, vortex flow, sort of somewhere around the 27th or 28th here, splits up into sort of two distinct vortices, and then eventually the reverse transition happens. Same thing has happened once in the southern hemisphere, only once in 50 years of observations, on the 23rd, I think, of September 2002. Just pick your favourite picture here. They're all showing the same thing, different concentrations of different chemical traces observed by a satellite in the top row, and the results of assimilating those observations into a chemical transport model in the bottom two rows. And you see the same thing. What starts out as a sort of axisymmetric vortex here splits there into a sort of wave 2 flow. And some people think, although I stared at this a lot and I can't see it myself, but perhaps you will be able to see it. Some people think the same thing happens on Venus, in the south polar vortex on Venus. The quantity plotted here is the oxygen air glow as observed by the Venus Express satellite. There's usually a dipolar vortex in the south pole of Venus. I think this has been known about for decades, actually, and it's pretty stable. So unlike the Earth's vortices, which are usually sort of axisymmetric and occasionally split, the south polar vortex on Venus spends most of its time in the split state, the dipole state. And, well, what apparently happens here, actually Fred Taylor puts it better than I can, the dipole coquettishly becomes a tripole for a while. I can't see it, but I think just about one can convince oneself that there's a tripole here. People
What are you looking at exactly, and how high up is it?
It's the oxygen air glow, so it's pretty high. It's pretty high in the atmosphere. The day side is yellow, of course. The night side is blue.
Atmospheric, well above the clouds.
Yeah. Anyway, people who've stared at this for longer than I have think that the wave 2 sort of anomaly became a wave 3 anomaly for a while. Now, I mean, the history of my involvement in this piece of work is that I was giving a seminar about those laboratory experiments, and someone in the audience, Thomas Berner, asked a question at the end about, well, he pointed out that these polar vortex splits, at least qualitatively, exhibit a strong resemblance to the sort of transitions we were seeing in the laboratory experiments. So just a rapid transition from one well-defined wave number state to another and then back again. So we began to wonder, Thomas Berner and I, a couple of years ago, whether there may be a conceivable interpretation of these polar vortex splits, both on Earth and potentially on other planets, as being noise-induced. In other words, induced by gravity wave noise, just as the regime transitions in the laboratory appear to be. So I'm going to pursue that idea in a simple conceptual model The classic model for stratospheric vacillations goes back to a paper by Hulton and Mass. They proposed, again, it's a quasi-geostrophic model which captures the non-linear interactions between the zonal mean zonal flow and a grave large-scale wave represented by U and X and Y, the sort of real and imaginary parts of the wave. And this is a bistable model. For a range of plausible parameters, there are two stable states in this model. One stable state has a large zonal mean zonal wind and a small amplitude wave, and the other stable state has the opposite. And in fact, we're not going to use the Hulton and Mass model, but a coarsely discretized version of it due to Rizhmaikin. So the Hulton and Mass model is vertically continuous in height, but these authors in 2003 very coarsely discretized the Hulton and Mass model in height. In fact, into only three values of Z, an upper boundary, a lower boundary, and one point in the middle. And so the X and the Y and the U here are the values in the middle box of the original vertically continuous U and X and Y. Anyway, you end up with this system of equations, a system with 3 degrees of freedom.
Additional variables for the lower and upper box, or are these just boundaries?
Boundary conditions, yeah.
It's just 3 variables.
Just 3 variables, yeah, that's correct. Interpreted as being the variables in the middle of this, in the middle of the stratosphere. There are 2 parameters I'm going to vary in these equations. A planetary wave forcing, this is a lower boundary condition. The lower boundary of the original model is roughly nominally at the tropopause. So this is the height, the amplitude in meters of the planetary wave forcing at the tropopause, and there's this lambda as well I'm going to vary, which is the vertical shear of a radius of equilibrium flow. These equations, so X and Y are clearly being damped, so is U being relaxed to a prescribed flow. There's X and Y oscillate at frequency R, and there's this quadratic nonlinearity which couples the waves to the zonal mean zonal flow. Now, these authors showed that the qualitative dynamics of this very coarsely discretized system are unaltered compared to the...
Where is lambda in the equation?
It's UR over delta Z, where this is UR. It's hidden in here. The qualitative dynamics are unaltered by this coarse discretization. So in other words, the vertical variations in the original model don't seem to contribute much to the qualitative dynamics. And critically, the bistability is retained, so this is a bistable system. So it's an ideal model in which to explore the possibility of gravity wave noise-induced polar vortex splits. So this is the regime diagram in the space spanned by those 2 control parameters. For small values of h, there's only one stable state, which is the state with a large value of u and a small value for x and y, so the large zonal mean zonal flow and a small amplitude wave. For small values of lambda, you have the other state being stable, and there's a wide range of values, combinations of values of h and lambda, plausible values of h and lambda, at which both those states are simultaneously stable. And I'm just going to show you now the equilibrium solution for u along this line. So picking a particular value of lambda, 1 meter per second per kilometer, which is a plausible value for this parameter, and looking at the variations with h of the equilibrium value for u along this line, and you see what you expect to see. The one stable state with a high value of u, this is the non-wave state, stable up to a certain point, and then at this bifurcation, so there's a third equilibrium solution here, of course, which is unstable. And then the wave state being stable for this range of values of h. Now, the classical interpretation of polar vortex splits in the context of this model is that you start out in the what is the axisymmetric state, and h is increasing in time, and eventually you fall off the edge of this when you reach the bifurcation point. And that is a deterministic interpretation of these polar vortex splits. It's just the planetary wave forcing at the lower boundary of the model growing in time and eventually kicking the system into the other state. I'm going to ask here whether it's plausible that gravity wave noise in this model can trigger a transition from the upper state to the lower state even before this bifurcation point is reached. So for values of h down here somewhere, is it plausible that a stochastic gravity wave drag parameterization in these equations could trigger that sort of transition with a reasonable value of the noise? And it turns out that it is. So again, this is a crude parameterization of gravity wave drag. I'm going to use additive noise in the evolution equation for u, but not in the evolution equations for x and y. Balanced and unbalanced flows are not thought to interact very strongly, which is why I've left the equations for x and y alone. But on the other hand, it is known that gravity waves transport momentum and deposit their momentum in such a way that it accelerates or decelerates the zonal mean zonal flow. So a natural way to crudely parameterize gravity waves in these equations is to use additive noise in the evolution equation for u only. It's not state dependent. There's no obvious reason to me why. So there are gravity wave sources near the surface of the Earth that don't seem to depend, to me at least, to a good first approximation on the state of this system. So it's not multiplicative noise, it's just additive noise. I'm going to ask the question, can additive noise here of strength, amplitude sigma a, and a typical value in the atmosphere is 1 meter per second per day. People who write gravity wave drag parameterization schemes say that a typical drag on the zonal mean zonal flow due to breaking gravity waves is about 1 meter per second per day, or the acceleration corresponding to the drag force. Can that sort of amplitude of noise kick the system from the one state into the other? And it turns out that it can. So here's a typical integration showing solutions for u, starting the system off in what is the axisymmetric non-wave state, integrating it forward in time. Of course, it remains here indefinitely if the noise is not activated. But when I activate the noise arbitrarily at time 1,000 days in this experiment, it does what you expect it to do. It wobbles around a bit, and eventually, after some period of time, it undergoes that transition into the split vortex state. This is for noise of 0.5 meter per second per day. The message to take from this result is that it is indeed plausible that gravity wave noise of the same amplitude as that seen or believed to exist in the real atmosphere can push the system from the axisymmetric state into the split vortex state when the corresponding transition would not have been possible without the gravity wave noise. So that I'm using h equals 200 here, so I guess I'm here. So the corresponding deterministic transition would require h to grow up to here. So what I'm saying is that gravity wave noise can kick the system from this state into this state before the deterministic bifurcation point, according to these experiments. This is called the first passage time, and of course if we repeat the integration with different realizations of the noise, we'll get different first passage times. The first passage time is a continuous random variable. It's a functional of the realization of the noise. When we repeat this experiment 1,000 times and plot the histogram of the first passage times, again for reasonable parameters, we can sort of estimate probabilities of the system having undergone a transition in a certain amount of time. And again, the message is that for reasonable values of the noise, there's a, well, I thought there it is. Sort of the median first passage time here is 70 days. So there's a sort of 50-50 probability of a transition within 70 days. Suggesting again that this is indeed a plausible mechanism. And of course, the louder you make the noise, the smaller the median first passage time.
Never see it go back.
No, I don't. No. I guess it would if the noise was. If you made the noise even louder, it might be loud enough to kick it back. I think it sticks in the. Yeah. So deterministically, what happens is h increase. You see the hysteresis. H increases, you undergo the transition, and then you go back along here. But in our experiments, because we're keeping h constant, it just drops down and stays there. You'd have to incorporate changes in h in the model, I think, to see the reverse transition. I'll skip over the rest of this, I think, except to say that we've backed that up with numerical integrations of the Fokker-Planck equation. So you just see probability density leak away from the one state into the other state as time evolves. Right. Now I'm going to talk about Stommel's mixed layer daemon before the end of my time. So, what's this all about? I mean, I think Tim put this up, certainly it's probably been put up in a few talks, this idea that the mean state in a system without noise is potentially different if there are sort of asymmetries in the potential well, in the energy landscape, different from the mean state with noise. And a possible mechanism, a physical mechanism corresponding to these asymmetries in the context of the ocean mixed layer was proposed by Stommel, or at least is related to a proposal by Stommel, who said the following in a paper in 1961. If you introduce a negative buoyancy perturbation at the surface of the ocean, it will convect to the base of the mixed layer and mix water and deepen the mixed layer. On the other hand, if you introduce a positive surface buoyancy perturbation, it will not have any impact on the depth of the mixed layer. So there's an asymmetry between the forcing and the response here. Does that make sense? So if you add some dense water to the surface of the ocean, it will convect down and mix at the base of the mixed layer and deepen the mixed layer. But a positive surface buoyancy perturbation will not do that. It will be mixed into the mixed layer, but will not change the mixed layer depth. And Stommel, by analogy with Maxwell's daemon in thermodynamics, this hypothetical daemon who stands by the trapdoor and only lets certain particles get through, Stommel said there was a daemon sitting in the mixed layer and only letting through the negative surface buoyancy perturbations and stopping the positive ones from getting through. This is a physical mechanism which can give you an asymmetry in the energy landscape here, because there's an asymmetry between forcing and response. Now, of course, in the real world, there will be air-sea fluxes that occur on timescales that are too fast and spatial scales that are too small to be resolved in coupled climate models. So this mixed layer daemon idea is a plausible mechanism which could be affected by noise-induced rectification. And I'll show you that. I have some evidence in a GCM experiment that is the case. So I'm going to run an experiment here, a coupled climate general circulation model. I'm going to stochastically perturb the evaporation minus precipitation, so just the moisture flux in this case, with uncorrelated in space and time multiplicative noise drawn from this uniform distribution. And I'm going to compare that integration, its climatology of its mixed layer and sea surface temperature, with the corresponding control run, deterministic control run. This is the GCM I'm using, these are its components, and I'm going to run two 100-year integrations. And a plausible conjectured sort of impact here is that precisely because of the mixed layer daemon, there will be a systematic, one might expect a systematic deepening of the mixed layer, because the negative buoyancy perturbations will deepen it, but the positive ones will not make it any shallower. That's the asymmetry, the daemon only letting perturbations of one sign down to the base of the mixed layer and deepening it. So you might expect sort of colder, deeper water to get mixed up and for that to cool the surface of the ocean. This will happen globally, but will be especially pronounced in the tropics, where the background mixed layer is at its most shallow. And because the warm equatorial ocean surface drives a Hadley circulation in each hemisphere, you might expect a weakening of the Hadley south, and all the concomitant impacts of that, such as reduced precipitation over the intertropical convergence zone, and perhaps increased precipitation in the subtropics. So that's my sort of conjecture for what we might expect to see in this GCM experiment, where we stochastically perturb the air-sea freshwater flux. And I think we do indeed see that. So here's the net upward water flux in the control integration from a paper that's about to be submitted. So you see the intertropical convergence zone, which is net precipitation, and the subtropical regions of net evaporation. And if I just flick between that and the anomaly, so the net upward water flux in the stochastic experiment with the control subtracted out, you see that there's there's an inverse relationship between these two spatial patterns. So where it rains a lot in the control run, where it's blue here, regions of precip dominating over evaporation, it's red here. And where it's red here in the subtropical regions where evaporation dominates, it's blue in the anomaly plot. So there's an anti-correlation there. And I believe it to be the case that the mechanism for that change in the mean climate is noise-induced rectification, and the physical mechanism that causes it is the mixed layer demon proposed by Stommel. And finally, in my final 2 minutes, I'm going through this a bit more quickly than I wanted to. I just want to talk about the excitation of El Niño oscillations in a coupled climate general circulation model. Jonathan Gregory yesterday talked about the famous model, which is a coarse resolution version of HADCM3. It has approximately half the resolution. And in fact, it's so coarse that there's no ENSO in this model. There is an ENSO in HADCM3 that looks reasonable, but in Famous is so coarse, even though the resolution has only been degraded by a factor of about 2, there's no ENSO, no El Niño cycle. I'm going to compare in my final slide, which is coming up next, 3 integrations of this model: a control run, they each last for 2,000 years, a control run, a run in which the vertical diffusion coefficient in the ocean mixed layer is perturbed by multiplicative noise drawn from this uniform distribution, and this time it's correlated in time but not space, and a third run which is the same but with depth coherent noise. I mean, the idea here is to crudely mimic the dipole mixing caused by mesoscale eddies, which are lacking, of course, in Famous. Famous is not an eddy permitting or an eddy resolving model. And this is a new result that just plotted a few days ago, so I haven't quite, there's a bit more digging to do, but so there are 3 curves here. These are power spectra of the Niño 3 index, which is the classical quantity one uses to look at El Niño and La Niña. The black is the control run, and you see that there is no peak in the El Niño power band in the black curve because Famous lacks an ENSO cycle. And what's interesting is that in the red and green curves, which show the noise correlated in time in red and also the noise correlated in time but also coherent in Z in green, have a peak in the right place where the black curve does not. So for some reason it seems to be the case that the introduction of this stochasticity on timescales of a few days has somehow excited power in the ENSO band that was missing in the control run. Now we have a bit more digging to do to work out exactly what's going on there, but I think that's an interesting result. Someone shaking his head in the audience. Anyone doesn't believe that. Anyway, so I've shown that noise-induced transitions are seen in rotating laboratory fluid experiments. That noise-induced transitions are a plausible mechanism for stratospheric polar vortex splits. That noise-induced rectification of the ocean mixed layer via this mixed layer demon proposed by Stommel is seen in an ocean general circulation model. And finally, very briefly, that ENSO oscillations appear to be excited by stochastic noise in a coarse resolution general circulation model that otherwise lacks an ENSO cycle. There's power missing in the ENSO band in the control run because the model is too coarse. I just finished by, can't really resist putting up a quick advert for this book, which Tim and I put together last year. Was it this year? Last year, based on the Filtrans special issue in 2008. That's it. Thank you.
This is the chance for any head shakers to ask
Well,
some questions.
he's left the room, so.
Irene.
For that last point, are you going to try different sorts of stochastic parameterization, just to see that it's not just a coincidence?
Yes. Yeah, as I say, this is hot off the press, really. I haven't had time to digest it yet, but yeah, further experiments are planned. Well, what's interesting is that it doesn't seem to matter whether there's coherence in Z. at least in the ENSO band. And of course, we need to assess the statistical significance of this, although it looks significant to me by eye. Yeah.
Michelle, do you have a question?
Yeah, I will ask next because I need to go back to my notes.
Okay, so let's take Hugo's first then.
Well, in the vortex splitting part of the talk, so you mentioned that basically in the northern hemisphere it splits pretty much every year, whereas in the southern hemisphere it hardly ever happens at all.
That's right.
So I mean, I think normally we think about this in terms of like to do with differences in planetary wave forcing.
Yeah.
But is there potentially a component of it which is to do with differences in gravity wave forcing?
Potentially, yes. The conventional explanation for that asymmetry is that H is larger in the northern hemisphere than the southern hemisphere, so it's easier to cross this deterministic bifurcation point. And this is something Thomas Bohn and I have thought about. It certainly is the case that the gravity wave field in the northern hemisphere is more highly energized than the gravity wave field in the southern hemisphere, just because there's more topography at the relevant latitudes in the northern hemisphere. So, not only is H larger typically for the Arctic polar vortex than for the Antarctic polar vortex, but also the value of the noise that we should think about adding is also larger, arguably. So, potentially that could play a role. I don't know if it does. It's plausible.
Yeah, also concerning the last slide with the El Niño oscillation. So there are two possible mechanisms how noise could trigger oscillations. One is it could feed oscillations that would otherwise damp out, and the other one is it could enable well hopping. So which mechanism is at work here?
I have no idea at the moment.
So there's also no knowledge about the underlying physics, that there are two wells or whatever?
I mean, there's a raging dispute, isn't there, about whether ENSO is a stochastically excited phenomenon or really due to nonlinear chaotic dynamics, internal dynamics. So I don't know the answer here. I mean, so what is known is that, I mean, just degrading the resolution by a factor of 2 completely suppresses apparently ENSO in this model. So what is known is that the propagation speed of equatorial waves is sensitive to the numerics. So the propagation speed of a Rossby wave on an Arakawa B grid differs from that on an Arakawa C grid, for example. So it's possible, and I don't know, I'm just speculating here, plausible that the degradation of the resolution by a factor of 2 has somehow slowed down the Rossby and Kelvin, equatorial Rossby and Kelvin waves. So I mean, there is this interesting power here in the control run at a period of about 10 years. So it might be that the Rossby and Kelvin waves are just going at half the speed they should be. I mean, that's a plausible explanation for this, I think.
There are some rules of thumb, aren't there, for the number of grid points per wavelength, and if Famous doesn't have it, it doesn't have it, and no amount of noise is going to help it resolve the Kelvin waveforms.
Right. Yeah.
So there's someone from Michael.
I was very impressed by the premature collapse that you got in the THC with some wind noise. Could you say a little bit more about that? The nature of the wind noise, perhaps? Was this something that you'd done? I can't quite remember the story now.
No, it wasn't. I'm going to struggle, I think, to give you a definitive answer. I'll try, though, if I can find it. Oh, come on, where is it? Here.
That seemed a very dramatic early collapse.
Yeah, that's right. I agree. What can I think I can't tell you anything other than what's written up here. Actually, it's a while since I read the paper. Lang et al. 1999. I mean, it's proper primitive equations, ocean general circulation model with idealized geometry. So the continents are sort of rectangular rather than.
Yes.
This.
Do you know the nature of the noise? Was it spatially variable, temporal?
I'm afraid I'll have to refer you to paper. Sorry. Yeah.
Where was it published? You have to...
I think it's probably Journal of Climate or Journal of the Atmospheric Sciences, but I can let you know.
I take it that's a non-eddy resolving model.
Yes, I think it must be. I don't think there were any eddy resolving models 10 years ago, really, were there?
Very close for long enough, wouldn't
Correct. Yeah.
Michelle, have you
In the Uzmaikan model, I mean, bifurcation diagram you show with the coexistence between one and two stable states.
Yes.
I fail to understand how you diagnose the boundary between one stable state and the two stable states. How in practice do you do?
In this diagram here?
Yes.
Okay, so you're concerned about the potential problem of hysteresis and whether these curves really are where they should be. Yeah, I see.
Yeah, it's painful to diagnose usually these things.
Yeah.
Quite intrigued.
I think. I think.
Through linear stability
Yeah,
analysis.
The equations to solve.
Oh, that's the.
This was
that-
just 3 equations.
Oh, it's
Yeah.
ordinary differential
Yeah,
equation.
yeah,
Oh,
yeah,
yeah,
yeah.
that's the crystal.
So it's possible for this system. Yeah,
Okay.
that's right. I can't remember if that's taken from Rajmaikin's paper or whether we did it. But anyway, yeah, it's yeah.
I thought of PDEs.
It's not that it's not difficult. It's easier than you thought. Yeah.
Are there any other questions? Okay, in that case, let's thank Paul.